In episode 40, titled Justify Cryptography Choices by Data Sensitivity and Risk, we treat cryptography selection as a risk decision anchored to the value of the data, the ways it can be harmed, and the capabilities of likely adversaries. Crypto is not a fashion choice or a checkbox. It is a control family that must demonstrably reduce confidentiality loss, integrity corruption, or authenticity spoofing at a cost and complexity the organization can sustain. The practical move is to start with what the data enables: payments, health, trade secrets, safety, and to ask what damage follows if an attacker reads it, alters it, or forges who said it. When selection flows from impact, threat, and feasibility, algorithms, modes, and key policies stop being abstract debates and become traceable decisions that leadership can defend and engineers can implement without ambiguity. Classification gives those decisions a spine. Begin by mapping each dataset to explicit requirements for confidentiality, integrity, and authenticity rather than treating all sensitive data as identical. Confidentiality asks who must not read the content. Integrity asks who must not be able to alter it undetected. Authenticity asks who must not be able to impersonate the origin or signer. Write the requirements in business terms first. Customer PII must not be disclosed to any party outside defined processors. Payment ledger entries must be tamper-evident for 7 years. Device firmware must be verified before execution. Then translate them into cryptographic needs. Where the class involves human subjects, regulated records, or safety systems, tighten tolerances and assume motivated adversaries. This explicit mapping prevents over-encrypting trivial telemetry and under-protecting records that would end contracts, trip regulators, or endanger people if mishandled. Encryption at rest only earns its keep when the keys are stored securely, separated from access paths, and managed with envelope patterns that compartmentalize risk. Envelope encryption encrypts data with a data encryption key, which is itself wrapped by a key encryption key stored in a hardened service such as a hardware security module, HSM, or a managed key vault with strict role separation. Access to data should not automatically grant access to keys. Operators who can read storage should not be able to unwrap the key material that protects it. Document how keys are generated, where they live, which services can request decrypt operations, and which audit logs prove those requests were authorized. When disks are decommissioned or snapshots copied, the design should allow you to cryptographically render data unrecoverable without trusting a single physical destruction process to go perfectly every time. When disks are decommissioned or snapshots copied, the design should allow you to cryptographically render data unrecoverable without trusting a single physical destruction process to go perfectly every time. Protecting data in motion starts with the protocol and ends with who is authenticated to talk to whom. Transport layer security, TLS, with modern cipher suites, properly validated certificates, and perfect forward secrecy should be mandatory for external and internal communications alike. Where mutual trust is required, service-to-service calls within sensitive zones, administrative interfaces, machine-to-machine control paths, mutual authentication via client certificates or strong token-based mechanisms is appropriate, with revocation and rotation that match the risk window. Avoid weak protocol versions and negotiate away legacy ciphers. Pin where feasible to narrow exposure to misissued certificates. The proof point is simple. Can we show, with captures and configuration proofs, that all high-value paths are encrypted end-to-end, both peers are authenticated to the required assurance level, and session compromise does not reveal past traffic? Public key infrastructure, PKI, makes asymmetric trust work at scale and must be designed, not assumed. Define trust anchors, roots and intermediates, under your control or a reputable external authority. Describe certificate issuance workflows that bind identities to keys with the right assurance. And enforce revocation paths via Online Certificate Status Protocol, OCSP, or short-lived certificates where latency to the truth matters. Automate renewal well before expiry to prevent outages. And bind issuance to verified ownership signals, domain control, service ownership in your inventory, device attestation to prevent misissuance. Separate roles for PKI administration, certificate requesters and approvers, and log every issuance and revocation to immutable stores. A credible PKI story explains who may vouch for whom, how that vouching is proven, and how bad vouches are undone promptly. Specialized contexts bring concrete configuration decisions. For databases, use transparent data encryption with AES in a mode suitable for storage. Keep master keys in an HSM, and rotate data encryption keys on schedule with minimal downtime. For file systems and object stores, enable server-side encryption with customer-managed keys, versioning, and object lock where retention rules apply, and layer client-side encryption for the highest sensitive content that must remain opaque to the platform. For backups, enforce immutability windows, sign manifests, and verify HMAC or signatures during restore pipelines, so integrity failures stop the job before data re-enters production. For tokens and secrets, use a dedicated secrets manager with dynamic credentials, short lifetimes, and per-use audit trails. Never embed long-lived secrets in code or images. Each context should end with a check. Where is the key? Who can use it? And what proves that use was proper? Cryptographic agility is your insurance against the future. Version formats and protocols so fields can carry ALG v2 without breaking consumers, and keep parsers liberal in what they accept within policy, while emitters are strict in what they produce. Maintain deprecation playbooks that name the suites to retire, the telemetry to confirm usage, the steps to migrate consumers, and the rollback plan if an unforeseen dependency appears. Track external deprecations, browser policies, operating system changes, library end-of-life, and tie them to internal deadlines so you are never surprised by a certificate type or cipher suddenly rejected in production. The question to answer is not whether change will be needed, but whether you can change without outage or security debt when the moment arrives. Validation closes the loop between policy and reality. Unit and integration tests should prove that encryption, decryption, and signature verification behave as expected across known good and known bad cases. Proofs of possession should confirm that entities claiming a private key can perform required operations. And configuration checks should compare live settings to your standards protocol versions, cipher lists, minimum key sizes, certificate chains on a schedule. For critical paths, run adversarial tests. Reject self-signed imposters, detect downgrade attempts, and verify that revocation or short-lived expiry prevents reuse. Store results as evidence alongside change tickets and architecture decisions so audits and future engineers can understand not only what you intended, but what you actually proved. Monitoring must treat cryptographic failures with urgency because they often hide behind "it worked yesterday" symptoms. Alert on expiring or expired certificates before customers discover them. On the appearance of weak ciphers or protocol versions at edges where policies should prevent them. On key reuse outside approved contexts. And on decryption or signature verification failures that exceed calibrated noise. Watch secrets managers for anomalous access patterns and key vaults for privileged operations at odd hours. Tie alerts to runbooks that name the temporary safe state deny by default, rotate the key, switch to a backup certificate authority, and the approval path for high-impact moves. Crypto mishaps are reliability events with security consequences. Handle them with the same production rigor as an outage. Documentation is the narrative that makes all of this traceable. For each protected data class, state the business objective, the threat model, the chosen cryptographic controls, and the evidence that those controls meet the need. Include why alternative designs were rejected, cost, interoperability, risk, what assumptions you made, lifetime of secrets, platform guarantees, and how monitoring will detect drift. Place decisions where future readers can find them, linked to the risk register entry, the architecture diagram, and the runbooks, and include review dates keyed to library and standard life cycles. Good documentation is not a lecture on theory. It is a map from data value to working controls that someone new can follow without guessing. In conclusion, move from principle to execution with 3 immediate actions. First, build a current crypto inventory that lists protected data classes, algorithms and modes in use, key sizes and lifetimes, protocol versions, certificate authorities, and where keys live. Second, propose risk-aligned upgrades where weak suites, deprecated hashes, long-lived secrets, or missing mutual authentication threaten mission outcomes, and attach owners, dates, and verification steps. Third, publish a deprecation schedule for weak suites and parameters with telemetry-backed milestones and tested migration paths so nothing breaks when the cutoff arrives. When cryptography choices are justified by data sensitivity and risk and proved by tests, monitoring, and traceable decisions, the organization gains durable protection it can explain, operate, and evolve. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.